Ever wondered how AI systems like GPT or BERT understand language so deeply? The answer lies in a revolutionary architecture called the transformer. Today, we're diving into the technical heart of transformers, how they process data, why they outperform older models, and the math that makes it all work. If you're a developer, researcher, or just curious about AI, this is the breakdown you've been waiting for. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated NLP. But they had a critical flaw: sequential processing. RNNs struggled with long-range dependencies, and CNNs couldn't capture context beyond their filter size. Imagine trying to understand a paragraph one word at a time: slow, error-prone, and limited. That's where transformers stepped in, rewriting the rules of sequence modeling. At the core of transformers is the self-attention mechanism. Let's break it down. For every word in a sentence, the model calculates three vectors: queries, keys, and values. Think of queries as what am I looking for, keys as what's available, and values as the actual data. The attention score is the dot product of a query and key, scaled by the square root of the key dimension. This score determines how much focus each word gives to others. For example, in the cat sat on the mat, the word cat might pay more attention to sat than mat, capturing semantic relationships dynamically. But wait, how does the model know the order of words? Unlike RNNs, transformers don't process sequences sequentially. Enter positional encoding, a set of sinusoidal functions added to word embeddings. These encodings inject information about a word's position into the model. The formula: for each position I dollar and dimension d backslash text p, I 2k backslash sin, I slash 10,002k slash d, and backslash text p, I 2k plus 1 equals backslash cos, I slash 10,002k slash d. This allows the model to learn relative positions, enabling it to handle dependencies across long distances. Once attention is calculated, the model uses a feed-forward network to transform the vectors. But here's the kicker: multi-head attention. Instead of one attention mechanism, the model splits the query, key, and value vectors into multiple heads, each learning different relationships. For instance, one head might focus on syntax, another on semantics. These heads are then concatenated and linearly transformed, creating a richer representation. This parallel processing is why transformers scale so effectively. Training a transformer involves masked language modeling and next sentence prediction. In masked LM, 15% of input tokens are randomly masked, and the model predicts them. But here's the twist: 80% of the time it replaces the token with a token, 10% with a random token, and 10% leave it as is. This forces the model to learn context from surrounding words. Optimization relies on AdamW with a learning rate scheduler, and techniques like gradient clipping ensure stability during training. Transformers aren't just a model, they're a paradigm shift. By replacing sequential processing with parallel attention, they've unlocked unprecedented performance in tasks like translation, summarization, and question answering. The math behind them is complex, but the result is simple: systems that understand language in ways we once thought impossible. If you're inspired to explore further, check the description for links to papers and code. And if you want deeper dives into specific parts, like how attention weights are visualized or the role of layer normalization, let me know. Stay curious and keep pushing the boundaries of AI. Thanks for watching. If you learned something new today, hit subscribe and ring the bell. The future of AI is here, and we're just getting started.